Welcome back to the Open Hardware Miniconf. So for the next session, we have Julien Goodwin, who is a veteran of Open Hardware Miniconf. He's been coming along for years. We've seen him before. And this particular subject is something that is very, very interesting to me. As you would have seen in my earlier talk, I had the on-screen display for my multimeter. I love the idea of connecting test instruments to the network and automating things. So Julien, please take it away.
Hi. So yeah, I'm Julien by day. I do tech operations at Google. I am once again doing networking. By night, I'm a bit of a time nut. I literally use an atomic clock as a footrest. I have a cesium clock that sits under my desk at work, basically being a foot warmer. My house atomic standard here at home is under my desk at home. I'm very slowly designing my own NTP server from the chip level up. A few years ago at LCA 2019, I gave a talk on designing the SBC, the single board computer, and getting that all manufactured. And at the moment, I'm designing the digitally controlled ovenized oscillator for it because I actually want to do something a bit better than the original prototype I did. I've also done stuff and continue to do stuff with Linux Australia, do some photography, do various other things. So, automated test equipment. Let's kick right in. Early digital test equipment, we're talking late 50s, early 60s through the 60s, started to have pins for I/O as environments, major research labs, universities were starting to get computers. They were usually just simple parallel BCD buses for data with individual pins for control, and users would provide their own interface. That's off an old piece of HP kit that I can't even remember what it is. Then, released in 1972, Agilent, HP, Keysight, choose your name, created the HP interface bus, which then became the general purpose interface bus, and then got standardized as IEEE 488, which is a multi-drop serial bus. It's about 8 megabit at absolute peak, but really don't try and do that. The connector stacks, it's a bit weird. You can sort of do star topology or straight bus topology. Don't try and get too fancy. If you try and stack 4 connectors on top of each other, you'll end up with a real mess because those are not small connectors. Commands are new line terminated ASCII. It is still extremely common on modern test equipment. This is a 50-year-old standard this year. Brand new test equipment designed, released, comes out with GPIB because it is the standard. They've got more modern interfaces, but the old stuff still exists. And in that era, it was actually used as an interface for hard drives, tape drives, etc. on HP and Commodore computers, although the Commodore variant is not basic GPIB. So I mentioned the commands are ASCII. A few decades later, in 1990, the command format was actually standardized as something now called Skippy, which originally just used in GPIB. Now, essentially any transport major equipment will use commands like this. If you look in documentation, you'll see a command sequence like : trigger, sequence, source. And what that means is trig is required, the GR is optional. The entire sequence section is implied if you don't provide it. Again, sour needs to be specified, the CE is optional. It's a little weird, but you get used to it pretty quickly. It's ugly, but it's a command format. And yeah, more modern interfaces will have RS-232 on a DE9 or USB. There is a test and measurement class for generic devices, but there's also basic serial class devices as USB serial or USB ACM. These on devices that are either made by major manufacturers or also support GPIB will almost certainly be the same command set. So once you have built support in RS-232, it'll probably work unchanged on GPIB. It'll probably work unchanged over a network socket as well. That, for example, is a Keithley multimeter variant that we'll actually talk about a bit later. And because they ran out of physical space, they dropped the GPIB port, but gave you an Ethernet port. So, as I said, there's lots of equipment that supports it. You've got pretty much any major piece of test equipment: bench multimeters, power supplies, DC loads, power sensors, frequency counters, SQL generators, oscilloscopes, spectrum analyzers, VNAs. It really is pretty much any piece of major test equipment that you're used to using. At least the higher end versions will have it as an interface option. Some more modern stuff will no longer have GBIB, but it will still support the same command sets through different interfaces. There's also, in HP terms, what's called system test equipment, and this is stuff intended for automated use. So it might have little or no local control, local interfacing, a front panel with a few indicator LEDs or nothing at all even. The two really common ones of these are what's called a data acquisition device, which are actually big switch matrices, usually in fact just a chassis for a big switch matrix that you then plug in a relay board or an RF switch board. Many of these can have built-in multimeters. They are usually called multimeters, although in practice they are just voltmeters. This turns out not to be a huge limitation in practice, but just by their very nature, doing current sensing is a bit more of a pain, so you would typically do remote shunts and measure the voltage over those shunts. There are system power supplies. The wonderful old HP system power supplies are great if you need lots of power, either lots of current at low voltage or high voltage. Their UI is not great, but they implement a lot of stuff on the GPIB interface, and you can control them that way. The other thing is they're often really cheap because the UI is not great, and if you're buying them used, you're probably wanting to use it yourself. This is where building a remote front panel, like John's multimeter example, you can make a much more useful tool for yourself. And those power supplies can be had for almost nothing, plus the cost of shipping. Unfortunately, those big old HP power supplies are extremely heavy, so the cost of shipping can often be quite significant. There are also system versions of other test equipment, oscilloscopes, multimeters, RF power meters. Those are rarer simply because people that spec the integrated test racks that they are for will tend to actually spec the full version unless they're space constrained, because you don't save much money. Next, talking to a computer. So historically, there were all sorts of forms: PCI cards, ISA cards, raw bus interfaces on some really old systems. These days, what you actually do is you use a USB interface or an Ethernet interface. Although it's surprising, it doesn't seem that any test equipment I'm aware of with both a USB port and a GPIB port will actually act as a GPIB interface, with the possible exception of some of the really grunty stuff that actually runs full desktop Windows. I suspect some of those can be made to be a GPIB host as well, but I've never tried that. You can get nice generic open source hardware GPIB interfaces. That's a Galvant GPIB USB. It's the sort I use. It works fine. Both Keysight / Agilent Hewlett-Packard and National Instruments are the two companies that are most known for GPIB equipment, have USB interfaces. The really big warning here is clones of those devices do exist. The clones are known to be buggy. It's a little hard to actually get good options, which sort of means unless you have a reason to use them, to use the Keysight or National Instruments tooling, probably just use the generic ones. And the generic ones are nice and cheap, so wonderful. Now, a second interface. So GPIB is great when I've got big test equipment, but what about more custom stuff? What about more weird stuff? I can get system temperature sensors, but they're big and chunky and not necessarily integratable. But we have this wonderful thing called I2C. So I2C created in the 80s by Philips as a way to simplify TVs, which were starting to add heaps of digital features and such at the time. So the way to connect peripherals to microcontrollers. It's now extremely common. When I was writing this deck, I thought to check, and my laptop has 11 I2C buses exposed to the kernel. It probably has more I2C buses than that. They're just not exposed to the kernel. And it really has become the de facto low-speed interface for pretty much anything. If you've heard of SM bus or PM bus, those are I2C variants. There are some limitations, though. You get up to 127 endpoints on a bus, but in practice, most chips can only be selected to a few addresses, so you very quickly run out of address space that you can actually use. There are bus switches to work around this. The notable case for that is some network devices where I2C is a standard interface for them, or multi-output video, again, where I2C is a standard for plugins. Long bus length can be a bit of an issue. As was mentioned in the previous talk, there are chips to help here, and it's an open drain bus. You really should try and share the same IO voltage, and you absolutely must share a ground. Again, we'll talk about working around this on the next slide. Now, one of the really nice things that's happened recently in the last few years is Adafruit have standardized a connector format called SMAQ, which is nothing more than a pinout standard for a JST SH connector. That means any I2C sensor test board, they just plug in and chain. It's wonderful. Adafruit themselves have many breakouts. It's certainly in the dozens. And this means if you just want to chuck a temp sensor on a project, it's really easy. The little board in the top right there is a TI Temp 117, which is an incredibly sensitive temperature sensor. It's a lovely little thing. Works wonderfully. It is an absolute bear of a chip to solder, as we'll see later. Now, as I mentioned, I2C, it's meant to be intra-board. Depending on your sort of project, you might want to use an isolator. In my case, I'm doing some pretty sensitive power supply stuff, so I want an isolator, even though I don't really need one. And again, if you're using cross-board, it's a way to avoid noise. If things are working and you're not doing very sensitive power rail or signal stuff, you might not need it. TI have an ISO 1550, 1560, 1540 series. Now, be careful if you're looking at isolators. Some of them care about where the clock is coming from. Some of them care about which side has a higher IO voltage. Just read the datasheet when you're looking this up. You don't want to design the board and realize, oops, that's never going to work. Now, computer interfaces. So, as I mentioned, my laptop has 11 I2C buses. Great, I can just plug into one of them because, well, it turns out display interfaces actually use I2C to do some sensing. So you can piggyback off that and you've got an I2C interface on your desktop computer already exposed to the world. It's not a great idea to use. On embedded boards, you actually have some buses that are intentionally exposed. Check if those buses are actually unused. Reusing a bus that's in use for a general purpose on a machine, you might have some issues. For my own test use, I simply used a USB breakout, even though I was using a Raspberry Pi, because it's just easier to be isolated. It also meant I could do my development on my laptop, which is a big chunky thing, over USB, and then just plug it into the Pi. And I don't really care that it's an extra step when I could be a little bit more efficient. If I was actually building a permanent install, sure, I'd be more efficient. But testing, let's solve the problem and move on, not be perfect. So my project was characterizing a DAC. As I mentioned, I'm building a digitally controlled ovenized crystal oscillator. And the digitally controlled, there's a DAC that does that digital control. I want to understand what the linearity is of that DAC as it is actually used in circuit. I then want to understand how that affects the output frequency. And unfortunately, I didn't get to that, and we'll maybe talk about that if we do have a few minutes. So here's the test board. There's the actual OCXO board in the middle, minus the oven, which is in the enclosure. And there's a carrier board. I originally didn't have the carrier board. However, I discovered that breadboards are terrible. And this is not really news to anyone who's tried to do even megahertz level signals. This is a 26 megahertz oscillator because that happens to be what I need. But it turns out breadboards are so terrible that they actually invalidated a bunch of my results. So I ended up designing my own board. And I'll make it clear, I didn't do any effort at signal integrity on this board. It is quick traces, everything just chucked where I wanted for quick layout. And it is massively better than the original board. So what is on the board? In the center on the pop-out board, you have the little silver thing is a crystal. The IC right next to it is the oscillator itself, which is a slewable oscillator. The IC in the middle is the DAC. The IC at the bottom is just some power supply filtering. The collection of passives to the left of the DAC are some output filtering. And then the silver pad you can just see to the right of the oscillator is meant to be the pads for a TMP 117. Unfortunately, they are really small. This is surprisingly hard to solder. And if I actually want to get one soldered, I'm going to have to learn to use solder paste stencils. This was reflowed by hand, but the paste is just an issue. I should have actually brought one of those boards to hand to see just how tiny it is, but it is really quite tiny. The carrier board simply has some power supply filtering. I also chucked an I2C isolator footprint set on that. As you can see, that's not populated because, well, it turns out you can't buy chips at the moment for some strange reason. So, oops. That is why there's also a non-isolated SMAQ QT port. And so my problem. And there's an output buffer because the oscillator board can't drive a 50 ohm load, and I want to be able to plug into some of my RF test equipment. So the actual test setup in this progress, because I need to test a DAC, I need to test its values. That's going to take time. Spare Raspberry Pi through USB to an I2C MCP 2221, as I mentioned, through an isolator to a TMP 117, just to have a temperature sensor because there should be one, to my test board. Test board is powered off a nice lab power supply. I half got through integrating the lab power supply, but it turns out I can't, even though I have a very nice one with extremely good power sensitivity measurements, it's not actually useful for rail measurements. So I couldn't really use it as a source of input. And I ended up just using it as an extremely nice 5-volt source. So I part automated it, but didn't really finish. Then there's a GPIB USB with a Keithley multimeter. Nice. It is actually a basic low-end Keithley multimeter, not one of their really crazy ones. And originally a Stanford research frequency counter, which was going to be to use the to actually then close the loop. And I do for DAC values, what is the output frequency? In the end, I had enough weird issues with the Stanford research counter that I actually retired it for that use and bought a very nice HP counter that you can actually see. That thing just there is a very nice HP counter that blew a power supply right after I got it. And by the time I got the replacement power supply, I had to actually clear everything up. So I haven't gotten around to finishing that part of the testing because, well, that was in the first round of testing, and underneath all that equipment was my dining table. So it kind of turned into a HP catalog photo shoot of equipment, and that's not even the worst case stage it got to. So unfortunately, I'm in a bit of a messy situation where I moved house in March 2020 and never quite got this room set up as a lab. So instead it became my office for the last 2 years, and it is a small house. I don't have another room for a lab. But yeah, big unfortunate mess, and helpful to have somewhere to eat dinner. So the test setup only lasted a few days. And the code. I'll put the actual full code file up somewhere useful because this is a summary and not complete, but it's actually most of the code. Essentially, there's Python libraries for the GPIB USB. Adafruit has the Blinker library set, which lets their CircuitPython interface code run on general desktop Python. And the two of them combined work fine in a single program. So I connect to the multimeter through GPIB. I connect to the I2C devices, the DAC and the temperature sensor, through the interface. Do some configuration of the multimeter, tell it to clear itself back to defaults, essentially go into voltage meeting, measurement, set the range to a fixed value, set the power line cycles so that it does the best measurement I can get it to do, turn off averaging, measure on a trigger, set the trigger to manual, tell the temperature sensor to turn on averaging because I do want it there. And then I simply do a loop of, for every value in the DAC range, set the DAC, let it settle for a little bit, measure the voltage, measure the temperature, and write it to a log. And that's just a CSV, and then I can graph the result on the CSV. So I can see that the real bottom of the range and the real top of the range, it's not so great. But actually, we're hovering around 0.1% absolute error, and relative, that's 0.04-ish% plus or minus, which, okay. I don't quite like that dip just before half scale, and it unfortunately turns out that half scale is extremely important, so I might do some design changes there, but I've got the information to do those design changes now. Yeah. And as I said, I would have liked to have closed the loop a bit and done frequency measurements using the actual DAC app, the oscillator output. Unfortunately, for reasons I didn't fully determine, the Stanford Research Counter got out of sync when I used it on GPIB. It was measuring, something was buffering measurements, and I didn't figure out why. And the new HP frequency, or comparatively new to me HP frequency counter, unfortunately dropped a power supply right as I went to actually put it in use. So I haven't gotten back to that project since all those repairs happened. Yeah. So that's test interfaces, test, and then putting it together into a system. And so any questions?
Thank you, Julian. I haven't seen any questions. There is still time if anybody wants to jump in and put questions into the questions section of the chat. What I have noticed is that a couple of people have been putting I2C detect dumps of their computers into the chat to show how many buses are exposed on their computers.
Yeah, and there's also a sysfs tree somewhere in /sys. There's a bus list for I2C, which is where I got the 11 number. It was just such an absurd outlier by comparison to all my other machines that it's like, how?
And what are they all doing?
I can only assume that both USB-C ports, the HDMI port, like 2 or 3 for sensing or something, and I still can't figure out what they're all doing, but
yeah,
somehow we have 11 other things.
Yeah. Well, perhaps there are some associated with drive controllers, maybe. Yeah, there are a few things they could be.
Yeah, exactly.
Yeah,
And
Bob just pointed out fan control. So, yeah, there are lots of things where I2C is useful inside a system. Yeah, so often with embedded projects, we're accustomed to having the I2C bus. There's one, not a dozen of them.
yeah, a
But
lot of
having
modern micros will give you 2 or 3. You might have to pin mux them or do other things. And as I say, you can end up in some weird cases where you end up needing 3 I2C buses for 3 devices because, oops, they can only do one address, and that one address is the same for all 3 devices.
Yeah. So I have a couple of questions for you since we have a minute or two, and I personally have an interest in this. So GPIB has been around for a very, very long time. And so just from my observation, not really knowing a whole lot about test equipment, it seems that a lot of vendors have been moving to like Skippy. And so could you explain a little bit about where things are now with modern test equipment that don't necessarily have those old style connectors on them?
Yeah, so modern test equipment will end up having USB quite often. Exactly what the transport is over USB can be a couple of things. And Ethernet for a lot of interface for devices where that makes sense, which tends to be anything that's expected to be in a sort of system integrated use is more likely to have Ethernet almost than USB. So the USB can be USB serial on some devices. On the sort of devices that would historically have had GPIB from that vendor, it's more likely to be the test and measurement class, which is a closer definition. I've not played with it, even though some of these devices I've used have USB ports that probably are class compliant because I have GPIB and I have the cables. This is in part the reason why test equipment for the last 15 years has still had GPIB ports, because we have the interfaces and we keep using them.
Yeah. Well, the follow-on from that, when we're talking about connectivity on devices, is how you pull data from multiple devices together into a single interface. And many years ago, of course, the standard for that was LabVIEW or various other pieces of software. So do you see basically what is the modern sort of equivalent to LabVIEW, or how would you go about that?
I've seen various attempts at it. The company that makes the power supply that's just on my shelf there, Evox, which is an open source power supply project, they've got an interesting little experiment thing. I don't know if it supports generic GPIB, but it's an interesting project that's sort of a, for those of you that have seen the various Python notebook style environments, it's a similar one aimed around test equipment. I would write Python because most of my uses are going to be run a test, and I probably want to run it headless somewhere where I don't have to listen to the fans of the test equipment.
Yes, and you probably want to be logging the data for future analysis. You're not necessarily sitting there watching virtual gauges move and that sort of thing, which is more what the LabVIEW UI is designed for.
Exactly. There is one trick that I did use that was really helpful. Although my multimeter actually has a scan card, so it has 8 inputs, I couldn't be bothered configuring that. But my multimeter has front and rear connectors. So I put one, and I needed one measurement from a different place. So I put it on the rear connectors, and my multimeter knows which connectors it's using. So at the start of the measurement, it would instruct the multimeter to switch to rear connectors, which is to say it would put on the display, switch to rear connectors, and I push the button. Because a nice feature on a bunch of test equipment is that you can make it a display, which means you don't just have to have the computer controlling it display things. You make the equipment you want to touch tell you which button to push.
Yeah.
So that was a cool feature. This is why there's an image on Twitter of my multimeter saying PC load letter, because I was making a very bad HP joke.
Cool. Okay. Now, are there any other questions? I'm just checking. We don't think we have any other questions from the chat. But thank you very much, Julian. That's been really interesting. This is a personal area that's really interested to me. I'm always trying to figure out ways to capture data coming off instruments and share them on live streams in particular. So things like capturing the scope interface and my multimeter and various other bits of equipment. So I think this is very useful.
The Evox software is probably the one I've most seen that seems like it would actually be really interesting. I'll dig up a reference to it and put that in the open hardware discussion.
That'd be brilliant. Thanks, Julian. Okay, well, thank you very much for your presentation. And everybody else, please hang around. We will have another presentation coming up starting, I believe, at 5 o'clock. So thank you, everybody. And thanks, Julian.